Okay, welcome back. Today we'll talk about some basic counting principles. And so the most important two notions here are those of permutations and combinations. So let's start with permutations. So what is a permutation? It's a way of arranging n given objects in all possible ways. So let's write this out formally. Here's a question: given n distinct objects, so where n is some number 1, 2, 3 and so on, some natural number, given n distinct objects, and often it's convenient to just think of those n objects as just being the numbers 1 to n, say the numbers 1, 2, 3 till n. Okay, so we think of this as being the following problem. You are given n positions, so denoted this way in a straight line, and in each position or box, what you want to do is to place one of these n objects, right. So the number of ways of doing this is given by sort of the usual counting principle, which is sometimes called the product principle. You first figure out how many ways there are of filling the first position, this first place here. There are n, you can put any of the n distinct objects. So here there are n choices for filling the first position. Now having filled the first position, if you sort of consider the second one, there are n minus 1 remaining choices. So now once you fill the first one, there are n minus 1 remaining choices. With the first two filled, there are n minus 2 remaining choices for the third position, and so on, till when you finally get to the very last position, you are more or less forced to pick the object that's left. So there's only one choice remaining. Okay, and the multiplicative principle or the product principle says the total number of choices is just the product of the number of choices at each one of these steps. So the total number of ways, total number of permutations of the numbers 1 through n is therefore n times n minus 1 so this is the factorial of n. Okay. So for example, if you take n to be 3, so you look at the three numbers 1, 2 and 3, and so the number of ways of arranging them in a line, there are 6 of them. So it's 1, 2, 3. So these are the three positions. I put 1 in the first place, 2 in the second place, 3 in the third place, 1 in the first place, 3 in the second place, 2 in the third place, and so on. And that's the full list. There are 6 possibilities. So that's 3 into 2 into 1, that is 6 choices, 6 permutations. Okay. So of course that's the usual well known answer, the n factorial. Now one important thing to keep in mind is that many of these sorts of problems regarding counting arrangements of various kinds often have equivalent problems which have a somewhat different description. Okay. So sometimes it's important to have a way of realizing that two different problems are really the same problem. So in the case of permutations, here's another problem which is really the same thing in disguise. So here's an example: find the number of n cross n matrices here again n being the same number n with each entry being 0 or 1. So sometimes these are called 0 1 matrices, every entry is 0 or 1 with the following condition such that each row and each column sums up to 1, or another way of saying it is has exactly it contains a single 1. Okay, every row has a single 1 and every column has a single 1, and a matrix of course is just an array of numbers or of entries. It has n rows and n columns, that is what the n cross n means. So in a sense it is like you have n positions, but right. So in all there are n squared positions to fill, but what one has is restrictions. You are only allowed to fill zeros or ones, and the sums of each row and each column is a 1. In other words, in every row there is a single 1 occurring somewhere, and every column there is a single 1 occurring somewhere. So what one does, so how does one solve a problem like this, for instance? Okay, so this looks seemingly different from the problem of permutations. Now to get a sense of this, so let us just see how one would try and do this. So imagine you had such an arrangement. So here is an example. If you did have, say, for n equals 3, you could put a 1 in the second place, so that row is taken care of. You can put a 1 here. So here is an example of a 0 1 matrix in which all rows and all columns have some 1. So how do you encode this information? Suppose you are given a 0 1 matrix like this. What we could do is the following. We could note down in each row the column number in which the 1 occurs. So for example, in the first row the 1 occurs in the second column, in the second row it occurs in the first column, and in the third row it occurs in the third column. So this matrix here we would encode as follows. You would write each row number and each column number. So you note down the row and column numbers of the ones. So for instance here in row number 1 the 1 occurs in column number 2, in row number 2 it occurs in column number 1, and in row number 3 it occurs in column number 3. Okay. So a 0 1 matrix satisfying the required conditions is the same thing as this data here, and observe that this thing here always has the following form. The rows are always going to be arranged as 1 2 3 till n if you are in the n cross n case, and what can change when the matrix changes, what will change is not this set of entries, you are always going to list them like that. What will change will be the column numbers, right. The ones may appear in different columns. So for instance, instead of this matrix, if you had say 0 0 1 0 let us say 1 0 0, if you had a matrix like this, then instead of this table you will construct a table in which let us say row column, row number 1, row number 2, row number 3, and in the first row the 1 is in the third column, the second row it is in the first column, and in the third row it is in the second column. So if you just see that the first thing is the same, so let us for now delete this piece of information, it is always going to be the same, it is always going to be 1 2 3. This matrix is really encoded by this sequence here 2 1 3, and similarly this matrix here is encoded by the sequence 3 1 2 and so on. Okay. So given a permutation of 1 2 and 3, think of putting those numbers in this the column numbers, think of putting them as the column numbers, and then the row numbers are 1 2 and 3, and then you can reconstruct the matrix. Okay. So I hope it is sort of clear, at least from this example, that the set of permutations and the set of 0 1 matrices are really, they have the same number of elements. Okay, and in fact there is a nice one to one correspondence between them. So on the one hand we have So let us just draw it schematically like this. You have the set of all permutations of 1 through n, permutations of the numbers 1, 2, 3 till n, and on the other hand you have the set here consisting of 0, 1 matrices with row and column sums 1, row column sums 1, that is the other set. Now what we have done according to this prescription here is really the following: given an element of this set, in other words given a permutation, so let us call it call the permutation something, say I will call the permutation as sigma, by which I mean sigma could be a sequence of 1s, 2s and 3s. For instance, sigma could be the permutation 1, 3, 2 if you are taking n equals 3, and corresponding to the sigma what you are doing is associating to it a matrix here. Let us call this matrix as A. So what's the association? Given 1, 3, 2, you construct a matrix A with the following property: A has a 1 in row number, well in row what? In the first row you will have a 1 in the first column. So in row column, so in row 1 you see what sigma is, that is a 1, in row 2 sigma is a 3, and in row 3 sigma is a 2. So these are the positions of the 1s, it is in the position 1, 1, 2, 3 and 3, 2, right. So that is the association. Now similarly, given a matrix satisfying those conditions, you can reconstruct the sigma in pretty much the same way. You note down where the 1s occur and then forget about the row numbers and just think of the column numbers as giving you a permutation of 1, 2 and 3. Okay. So things like this. So what we have done really is establish a 1-to-1 correspondence between this set here and the set of 0, 1 matrices. To everything here you have associated something there, and there is also an inverse map. So this is what you call a bijection. So what one has really done here is established a bijection between these sets. So recall the term bijection means that it is a map between two sets which is 1-to-1 and onto. So this is a 1-to-1 and onto function. But more simply stated, all it is saying is that you have a correspondence between elements here and elements there. Okay. Every element here corresponds to something there, and similarly every element there corresponds to its inverse. So when two sets are in bijection, they of course have the same number of elements. So the number of matrices which has that property is exactly also n factorial. Okay. So the number of such matrices is also n factorial. So this notion of bijection is rather important. It will come up again and again when one is trying to work with counting problems. It allows you to sort of recognize a somewhat more complicated problem as being the same as potentially a simpler problem. Okay, so I just talked about permutations. The other important notion is those of combinations. So combinations, again the typical problem here. So here R is some number between 0 and n is a number that's let's say at least 1. Okay, so given a set of objects and the combination is not ways of arranging but rather just ways of choosing R out of these n objects, and again this is I presume something that you must have seen before. So the way to solve this problem is sort of by going through permutations. So what this really amounts to is to say, well, let's take let's arrange these n objects. So here's the n positions. You arrange these n objects in all possible ways. So you look at all possible permutations, and once you have a permutation you just choose the first R elements of that permutation. Okay. So choose first R elements. and sort of put them in your basket. That's the choice you will make. So the question is, of course many different permutations will lead to the same choice of these R elements, right. So how many different permutations will lead to the same choice of R elements? Well, the answer is, if you take a permutation, you're given some permutation, and now you construct another permutation in which you permute these first R elements, okay, you permute them any which way you want, then in that new permutation that you generate, the first R elements are still the same, they are just occurring in a different order. Similarly, if you take a given permutation and then you construct a new permutation by permuting the remaining n minus R elements. So here are the n minus R elements that are not chosen. Now you permute those n minus R elements in any order you want. The final choice of R elements that you are going to pick will remain the same, because you are only going to worry about the first R elements, okay. So what this argument says is that, well, you have n factorial permutations in all, but out of those R factorial times n minus R factorial R factorial is the number of permutations of these R objects, n minus R factorial is the number of ways of permuting these n minus R objects. Now that is the amount of repetition that you have when you count these, okay. So the final number of distinct choices of R elements that you can generate from the set of all permutations is just n factorial divided by R factorial over n minus R factorial. So this is now finally the number of choices. So again, like I said, I hope this thing is somewhat familiar from before. So this number is often called NCR, so number of combinations of R objects out of n objects. And so again, just like I mentioned in the case of permutations, often there are other problems which are really problems of this nature in disguise. So here's another problem. You have, say, two alphabets A and B. So let's imagine I have two letters A and B, and what I want to do is to construct words of length A, of length n. So find the number of words of length n which only use the letters A and B, and we are given some further conditions such that which contain exactly R A's, R occurrences of A. So to get a sense of what this means, so let's take an example. Suppose I take n equals 5, R equals 3, what this wants what this is asking for. So let's take something slightly simpler. I say 4 and 2. I want words of length 4 which contain 2 A's. So for instance, a word which has 2 A's, so a word is just 4 letters strung together, that's what the word of length 4 means, and I want 2 A's amongst these, so which means the remaining 2 are B's. So here's one choice, here's another word, here's another word. Now similarly I have BA BA, and let's see, what do I have now? I have BA AB. Okay, so what we have done is written down a list of words which have length 4 and which contain exactly 2 A's, and there are 6 of them, 6 such words, and hopefully I've gotten everything right. There aren't any more words that one can construct. Now as written, this doesn't quite seem to be related to combinations, but one can actually think of this pretty much as the following problem. Imagine you have 4 positions which are to be filled with A's and B's. Now what you want here is to figure out how many ways there are of filling it in with exactly 2 A's, for instance. So out of these 4 positions I need to fill 2 positions with A's, and so if I just number the positions as 1, 2, 3 and 4, to obtain a word like this, all I need to do is figure out which 2 positions will be filled with A's. So each word of this kind gives me the following piece of information. It tells me 2 positions. So this is the same information as the 2 positions which have A's in them. So for instance, the word AABB has A's in positions 1 and 2. So you should think of AABB as corresponding to, so let us just write this out. So here are the 6 words we wrote out, and AABB has A's in positions 1 and 2. So I think of it as 1, 2. This is ABAB has A's in position 1 and 3. This has A's in position 1 and 4. This has A's in position 3 and 4. This is 2 and 4. And this has A's in position 2 and 3. Okay. So a word like this is really the same thing as a choice of 2 positions. Okay. So what is that? That's equivalent to the following thing. You are given 4 numbers 1, 2, 3 and 4, which are the position numbers. Amongst them you have to pick 2 numbers, which are the 2 positions where the A's occur. So the number of choices is therefore again number of words is the same as the number of choices of 2 positions, which is 4C2. Okay, which we know to be 6. So one can just compute. It's 4 factorial divided by 2 factorial 2 factorial. Okay, so now this business of words is often an important thing to keep in mind. It occurs in many different places. So, well, including in this usual identity that one sees in algebra. So if you want to compute, for example, a plus b the whole squared or a plus b cubed and so on. So that's something that one often does. So just think of a and b for now as variables. So we are often interested in trying to find how this expands out a plus b whole power n. Now we will just do this by example. We will look at a plus b whole squared. So that will just give you the well known identity. I have a plus b times a plus b. But here's I'm just going to do it with a slight change. I'll just I'll use the distributive law. I'll write it as a times a. So I'm not going to write it as a squared for the moment, plus a times b plus b times a and plus b times b. Okay, and of course you recognize this is a squared plus b squared plus 2ab. The only difference now is I have written it out like this without using the fact that AB is the same as BA. Okay, I want to for now keep the distinction. So let us not use. Let us not use the commutativity property. In other words, let's not use this property AB equals BA. So again, if you want to compute a plus b cubed, it's a plus b squared further multiplied by an a plus b. So I know what a plus b squared looks like. To that I need to sort of attach an a on the right and a b on the right and add them up. So it's AAA, ABA, BAA, BBA. These are the 4 terms which I get if I attach an a to the right of these 4 terms, and then if I attach a b I get plus AAB plus ABB BAB plus BBB. Okay, so that's a plus b whole cubed. And again notice it's just a familiar identity. If you use AB equals BA, if you think of a and b as being commuting variables, this is a cubed plus b cubed plus, let's see, a squared b, These 3 terms are just really a squared b. Similarly, these 3 terms are AB squared. Okay, so that is again the familiar identity. So observe, this is sort of suggesting the following thing. So observe, I just wrote out all the words there with 2 A's and 2 B's. So this is not quite that, but it's sort of clear from looking at what we are doing that here what I have obtained is all possible words of length 3 in A's and B's. Okay, I have written every possible word of length 3 in A's and B's. So the next step is of course length 4, but it's sort of clear by doing this repeatedly that a plus b whole power n is going to give you the following. This is just the sum of all words of length n in A and B, right. So observe, a plus b squared is just there are four terms which are basically all possible words of length 2. Here there are 8 terms which are all possible words of length 3 and so on. In general you have 2 power n terms consisting of all possible words of length n in A and B. And now here's the thing, if you now use the commutativity property, so let us see how this will, let us now allow ourselves to use the fact that you can move the A and the B past each other. If you do this, then what happens is the following. Okay, so we allow ourselves to use AB equals BA, then what happens is the following, that many of these words will now start collapsing into one. For example, here words which have 2 A's and 1 B will all become A squared B, right. So in general it's going to be an expression. So the question is, suppose I want to know, I have say A power r B power n minus r. So I want to know what's the, how many times does this term occur. Well, every possible word of length r of length n which contains r a's and n minus r b's, every one of them will collapse to give you the same term. Okay. So the coefficient of this thing here is just the number of words, the total number of words with r a's, with r occurrences of a's and n minus r occurrences of b. But that is exactly the thing that we have computed. So this is the sum now over all possible choices of r. Okay, so that is what this is going to become, but this is exactly the thing that we computed. We said, well, in general there I did 4 choose 2, but it is clear in general what it is exactly n choose r, because a word of length n in which you have r a's is just determined by the positions where the a's occur. So this is just n choose r, okay, or NCR, A power r and that is exactly what we call the binomial theorem, right. So that is indeed the binomial, which tells you how to expand A plus B power n, and this sort of gives you a much clearer idea as to how these numbers which really appear when you try and do a counting of certain types of configurations, why do these, the numbers of combinations, appear when you try and do this algebraic identity, when you try and expand this identity. The reason it appears is because it really counts all words of a certain kind, and that is exactly given by the number of combinations. Okay. So next time we will sort of look at some further properties of combinations.